Hey there. So I'm going to take you back to previous years in high school, grade 10 and 11 specifically, and remind you that you were introduced to optimization problems in that used to fit into the quadratic relations unit. So one of the questions you would have seen in the past was something along the lines of a hockey team that plays in an arena, and we have a capacity of 100,000 people who can actually buy tickets and come watch the game. If we sell tickets at $15, then on average we get about 50,000 people attend the game. But what owners, I guess, realized was that if they lowered the ticket price by $10, not by $10, by $5 down to $10, then the average attendance would actually rise to 65,000 people. So based on sort of that relationship, the question that you were posed in the past would be, how would you price the tickets? What would you set the ticket prices to be in order for the organization to maximize their revenue? And so when you heard the word like maximize, you knew that that was an optimization problem, and you were essentially trying to find the highest possible value that you could get. So these were sort of the rules, general rules back in grade 10 and 11 of how you knew how to solve an optimization problem. You always have to start by defining a variable, making a let statement, and then because this was in the quadratic unit, you essentially created a quadratic equation given the information, and then you modeled it with that equation. So your ultimate goal for that quadratic equation was to find the optimal value, which of course we know is the vertex, or it's attained in the vertex of the quadratic. So ideally, it'd be great to have the vertex form because the answer would have been basically given to you, but usually it would have been in factored form or in standard form. Now, if it was in either one of those forms, you had a few options. If it was in factored form, you could have found the roots, averaged the roots, found the axis of symmetry, and then from there plug that into the equation, and there's your optimal value. You also could have taken, well, if you had the standard form, then you didn't get the axis of symmetry right away, but you could use the little shortcut from the quadratic formula and just do the negative b over 2a portion, which would have given you the x value of the vertex. And then you could have put that into the equation to get your optimal value. Alternatively, if you didn't want to use the shortcut, you could have just used the entire quadratic formula, but that would have been more work. And then, of course, you go back to the averaging the roots process. The final way in grade 10 or 11 you would have done this was by, if you had it in standard form, you would have completed the square and that put it into vertex form. Again, all very algebraic procedures, but all of them would have got you the final answer. So if we were back in grade 10 or 11, this is likely how you would have solved the problem. You would have, and when I teach it, I will say, okay, the first thing you want to do is make your equation statement. What are you required to maximize? So RT maximize stands for required to, and then you're either maximizing something or you're minimizing. In this case, we're maximizing revenue. So we knew a formula for revenue was how many, in this particular case, how many tickets we sell. Actually, that would be the number of attendance, the ticket price, and how many tickets we sold. So how many people came and how much was each ticket that they made. So that would have generated our revenue. Now, when you first were introduced problems like this, I would have recommended you use some sort of chart like this. So a chart might have defined the scenario that was happening. So we knew that the ticket prices were decreasing by $5 at a linear rate. So what we were told initially was if we sell tickets for $15, we had 50,000 people coming to the game or to the arena. That meant we had no price decreases. That was our initial kind of thing. We're thinking about the initial price where nothing has changed. We fixed our price at 15. And then we said, okay, well, what if I decreased the price by $5? So now how many price decreases would I have had? 1. And what would our new ticket price be? $5 less than 15. So essentially you would have said 15 minus $5, and that's where the 10 came from. And what did we do to the number of attendance? We would have said, okay, well, that was taking, we knew it would increase by 15,000. So I added 15,000 to get the 65,000. Now, these are just the revenues that you actually would have made. And we're trying to actually maximize revenue. And look what happened. Revenue actually went down after I decreased the price by $5. Interesting, but let's not worry about that right now. So then you kept on the pattern going. You said, okay, well, what if I had two price decreases? So how did I get $5? I would have said, okay, well, 15 is what we started with. Now we're doing -5 times -5, which is the same as 2 times -5. And that gave us $5. But what did we do to the attendance? We started with the 50,000 and we added not 15,000, but two increments of 15,000, which is 30,000. Two increments of 15,000, and that's where we got the 60,000 from. So if we kept the pattern going, dot, 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 what would have happened was if I defined this as my variable, so now I need to think of a let statement. What am I doing? Number of price decreases. So it decreases never, decreases once, decreases twice, dot, 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 decreases, let's say n number of times. So we're going to let n be the number of times I decrease the price by $5. So what happens here, the ticket price in general would be $15 minus n increments of $5. So this would be your ticket price, an expression that represents it. The number of attendants could have been considered the 50,000 that we started with, and then we were adding n increments of 15,000 people. Okay, so that would have been how we would have set up, well, we would have defined our variable and our ticket price and number of attendants. So then when we defined that n, let's talk about that for a second, because when we defined that n, we defined it as the number of price decreases, number of $5 price decreases. But that's essentially could have been said, because there's an n over here as well, like this is this n, the number of price decreases, that's what this n stands for. But this n is also in the equation. But in this case, this is not about price, this is talking about attendance. So essentially your n could have been defined as the number of $5 decreases, or it could have been defined as the number of 15,000 spectator increases, which are very hard to say. Those aren't really easy to flow, let statements. And so that's ideally why we want to shift our way of thinking in calculus and get out of that, because no one normally talks like that. Nobody says, oh yeah, let's figure out how many times we should decrease the price by $5. Nobody wants to say that. They want to say, let's find out how much we should sell the tickets for, right? That's what we would say. And so that's where calculus is going to come in. But let's go back to grade 10. Let's finish this question, how we would have solved it in grade 10. So we would have come up with a revenue equation, and revenue is basically how much you're selling a ticket for times how many people came. So if I just took these two brackets and put them together, essentially I'm getting my number of my revenue equation. Okay, so here's my revenue equation: number of attendants who came times the ticket price. Now, if I wanted to know, so this is now I'm going back to my grade 10 strategies, right? So which strategy here would I use? I have it in factored form, right? I had two brackets beside each other. So the easiest way to do this would be to average the roots and get your axis of symmetry, and there's your optimal value. So in grade 10 or 11, you would have, so we would have found out what the roots were first. So let's set these two factors equal to 0, okay? And then each n gave me my two roots, so 3 and negative 3.3. Now, if we think about this in terms of a parabola, because this is a quadratic equation, this is going to be a parabola, and our equation actually has a negative n squared term, okay? Even though you don't see it because it's not in standard form, because of this -5 and this positive 15, it would actually have a negative leading coefficient. And you know that a parabola with a negative leading coefficient is just an opening downwards parabola. So I'm actually going to do a little bit more algebra here to find the axis of symmetry by averaging those roots. And I get this negative value. So let's just think about what that means for a second. So my roots were 3 and negative 3.3. So negative 3.3 is about here, negative 3.3, and 3.3 is somewhere over, or sorry, 3 is about here. So averaged is actually a negative value. But if I think about my x and y axes, in this case n and r axes, n was the number of price decreases. Well, if I got a negative 0.16 axis of symmetry, then my parabola would look something like this. Here's root number 1, here's root number 2. I guess I'm not really drawn here nicely to scale, but 3 should have actually gone over here. Move this over. So 3, the average would be negative. Now, what does that mean? What does that negative actually answer mean? That's not the negative revenue. That's not the price you're selling it for. It actually would mean, so think about it for a second. Pause the video if you want to think about it longer. Pause it right now if you want to think. A negative value actually means you didn't have a price decrease, you actually had a price increase, didn't you? Because if you got positive 16 or positive 0.16, that would have said you increased the price by 16 cents. So anything to the right of this origin would have been a price decrease, but anything negative would actually be the opposite. So it's an interesting thing, which means we shouldn't sell the tickets for $15. We should actually increase that price by 16 cents, thus making it what, $15 and 83 cents? Where did that come from? 1583. Hold on. Oh, I skipped a step. The big step. We have to go figure out the price. Which one of these gave us the price? So your equation was ticket price times number of attendants. So if I know I'm going to increase my price by 16 cents, let's go back here to my ticket price equation. So 15 minus 5 times n. We now know n is negative 0.16. And so my ticket price is going to be $15, and then there's your plus, and there's where the 83 cents comes in that I showed you already, right? So if you actually substituted that the end that you just solved for into the ticket price, you would have actually got $15.83. So that's where the price would have been or should be in order for this organization to maximize their revenue. So hopefully that sounded somewhat familiar. It should have anyways, because you would have done problems like this back in grade 10 and then again in grade 11. But every method we used here was methods we learned from quadratic equations from grade 10 and 11. So we used roots, we used the concept of the parabola, we found the axis of symmetry. But what we want to do is we want to broaden our horizons and move into the world of calculus and figure out how can we answer this question now using calculus strategies. So, right, so now that we're older and wiser, we can actually solve this problem using derivatives. So think about it. If you want to pause the video and just stop and think for a second, can you think about how we're going to use derivatives to help us solve this problem? Pause the video, just think about it, and then come back. Okay, so hopefully you pause the video. But before we actually figure out how to use derivatives and what aspect of it we want to do, we need to first think back to that let statement. So the problem was I didn't like hearing myself say, let n be the number of price decreases. That just doesn't sound right. So instead of saying that, the more common thing that we want to see, especially in the business world, they use the term, they define the variable n or x as not the number of price increases, but the number of units that were actually sold. So in this particular case of the hockey thing, it would be the number of tickets that you actually sell. So x would be the number of tickets sold, not the number of times you decrease prices. So that's what we want to get to. We want to shift our way of thinking, where x is the number of units sold. And then what we want to do is not create just any random quadratic function. We actually want to create any function. It doesn't even have to be quadratic, but we're going to call that function a demand function. That's the business term for it. Some people will also call it the price function. So between those two, that is what we're going to define. Now, because we actually call it a price function, we use the letter P, and we say P of X is that demand function or price function. But notice that we actually use the lowercase letter p. We don't use capital P of X because that we usually tend to refer to or think of as a population or things like that. So we don't use capitals, we use lowercase p's. Okay, so P of X is your price function or your demand function, where X is going to be the number of units sold for whatever the scenario is. Okay, so by formal definition, a demand function, I'm going to use the lowercase p of x, is the price per item at which X number of units were sold. So P of X is the price per item times how many items are sold. Actually, I just realized that doesn't sound right because that's revenue. Price per item times number of items sold. The price per price per number of items sold. Sorry, I just realized I messed that up. Price per number of items. That's your actual definition for price, for the price function. Okay. Now, because we want to link this to revenue, let's actually think about this. This can actually be thought of saying as the average price per item based on how many items you actually sell. So your formula would actually be, your relationship, I guess, would be between the price and the revenue. So total revenue divided by how many items that you sold. So this would be your formula, R of X divided by how many items were sold. So if you wanted the price function P of X, it should actually be a lowercase p, then P of X is R of X over X, and a simple rearranging for revenue would be X times P of X. Again, I meant these lower p's. Sorry, lower p's. Okay. So if you need to pause for a second, just absorb what I just said, rethink what I just said, make sure it all makes sense about where we come up with this formula. And then we're going to revisit that same question and try to answer that question using calculus methods. Okay, so pause if you need to, just take a minute and absorb what I just said. Okay, so now we're going to revisit that original question, and we don't really need this chart anymore. I'm just going to use it to start us off and get us back to where we were, where we want to introduce our calculus concepts. Okay, what we want to do is not create just a random revenue function that's going to be quadratic. We want to create a demand function. That's what the question is going to ask you. It's going to say, create the demand or price function for the following problem. And then all they're going to give you is that whole problem about the hockey arena. So if you did this the same way you did before, this ticket price, this relationship here, just this half, was actually the P of X you want. That's your demand function. But the problem is that demand function is in terms of N, where N was this weird thing, the number of $5 decreases, which doesn't sound right. We want this N to actually be an X, but we want X not to be number of times it decreases in price, but we want X to be the number of tickets that are actually sold. Okay, so I can't just replace N with X and assume X is the number of tickets sold, because X is not. This 15 minus 5N is a relationship of the ticket prices and the number of times you reduced the price by $5. So how can I make this N, what can I do with this N to now somehow incorporate the number of tickets that were actually sold? And if we look over here in this column, this little relationship, this expression is actually is an actual equation, that expression that represents the number of attendance, which is essentially the number of tickets that were sold, were they not? Right? So X is defined to be the number of tickets sold. So we can actually let this expression right here, the second bracket we had, actually be the X that we want here. So if we did a little bit of rearranging for N, because this N we want to get rid of, and we want to replace it with something that has an X in it, let's take this N and rearrange. So just using a little bit of Sam Deb, I'm going to move my 50,000 over and divide by 15,000. So if I isolate this N, that N is going to be X minus the 50,000 divided by that 15,000. So there is an expression that actually represents that takes the place of that N. So I'm actually just going to do a page here for a second so we can keep that in mind. And then let's use that. So actually that's what we just did here. So I'm going to come up with my price function. So I know my P of X was originally 15 minus 5n, but now that I have an expression for n, I can replace this n with the, with the x minus 50,000 over 15,000 that I just have. And that is actually your price function, your demand function. But I'm going to ask you on a test to make sure it's simplified fully. So, sorry, I forgot. I'm going to ask you to make sure you simplify this fully. So when you're doing that, this is just algebra. So why don't you pause the video and try to simplify this fully so that it's expanded and fully simplified. So no brackets, okay? So pause the video, try the algebra, and I'll meet you back and make sure we got the same fully simplified equation for the price function, okay? Okay, so did you get the same simplified expression? You might have made the 95/3 a decimal, it doesn't matter. This is your exact equation. So this is what the demand function looks like. So this is your price per number of tickets sold, where X is the number of tickets that you sold, or the number of people who attended. So remember what we're trying to do. Our ultimate goal is trying to maximize revenue, right? So this equation, as we see it right now, is actually linear. Agreed? The exponent on x is 1. So this is actually a linear equation. If you graph this function, it would be a line. But we want to come up with a quadratic equation because revenue, we want to maximize revenue. We know we want to make a parabola of some kind. So we were looking for the maximum of that parabola. So the revenue function, if you think back to the formulas we were deriving earlier, remember the revenue expression was equivalent to the number of tickets sold times the price per ticket, so XPX. So because we just found P of X, if we multiplied X times that P of X, 95/3 minus X over 3,000, there now is a quadratic equation, because if you were to expand the whole thing out, in fact, why don't we do that? Expand the whole thing out, and there is your, actually I'm going to move the order over as well, just so you can see the quadratic term first. So multiplying X times negative X over 3,000 is negative X squared over 3,000. So there's your quadratic term. Notice that it's also negative, which obviously means it is definitely a parabola opening downward, and this is the maximum we're trying to figure out, right? So this is what we're trying to do. And then we're going to have plus the 95/3 X. So we're ultimately trying to maximize revenue. Now, drum roll, where does the calculus come in? So, I just said this actually. I skipped all this, I already did this over there. Okay, so where does the calculus come in? If we want to find out this maximum value of any parabola or any function, then we know that if we find the derivative of the function, the slope of that tangent is going to be 0, right at that maximum. And so how do we find the slope of that tangent when it's horizontal? We're going to find the derivative of the revenue function and set it equal to 0. And when we find that equal to 0, we're going to get that one spot where the tangent line is horizontal. So let's do it. Okay, let's actually do this here. So if we find, I need the derivative equation. Or sorry, the revenue equation. Here's the revenue equation. So actually you're going to pause the video right now, and I'd like you to take the derivative of this expression carefully and then set it equal to 0 and find X. Okay, and we'll talk about what X is as soon as we meet back. So go ahead, and I'm going to do it as well, and we'll meet back. Okay, so hopefully after you found the derivative and set it equal to 0, you got 47,500. Now think back to what X was. And what does that represent? What does this 47,500 represent? X was the number of tickets that were sold. In other words, number of attendants, people who attended. Now that didn't answer the question. The question originally, if you go back to the original question, was what should they set the ticket price to be in order to maximize the revenue? So where am I going to put this number of tickets sold to figure out how much they should, what will they set the price to? And this is a more realistic situation. If I know that I sold 47,500 tickets and I just want to know how many, what I should sell my tickets for, I'm going to put it into my price function. That's what my demand function was. So if I evaluate the price function at 47.5, I will get the price, because that's what P stands for, the price per ticket sold. So 95.3 minus, and if you put the 47.5 into the equation for the price, I'm putting it into this one right here on the previous slide. And if I divide that by 3,000, put this all into your calculator, and guess what we get? It's a very familiar sounding $15.83. Okay, so that is what the ticket price should have been set at in order to maximize the revenue. And that answers our question using calculus methods. So I'm going to stop here. That was a little old, a little new. And what I'd like you to do at this point is try to do this problem yourself. Where is it here? Okay, so there's another question here. There's two, and you can find those on your on the handout. So there's a blank handout on the Google Classroom. There's one question here about the vacation company, and then there's another question here about Shelley selling seashells, seashell necklaces by the seashore. So two different questions. What I'm going to suggest you do is try them both using the strategies I just showed you. If you need to go back and rewatch the video, feel free to. And then on when we meet each other next in class next week on Monday or Tuesday, we will take these two questions up and make sure you got the right answer. All right, so good luck, have fun with that, and I'll see you on Monday. Bye.